Hello, hi. In today's video, I'm going to look at set operations. Consider two sets, call them A and B. There's sort of three cases that we can have for the way these sets are laid out. Either we could have B completely contained within A, or we could have A completely contained within B. Okay, we'll call that case 1, being completely contained in the other set. Case 2 is for the two sets to be disjoint, no elements in common. And then case 3 is for the two sets to have some elements in common, but not all. Okay. These sets, there can be there's three operations I'm going to look at. The first operation is intersect, A and B. The second is union, A union B, A or B. And the third is set subtraction, so A minus B. Or you could think about it as A without B. So I'm going to go through in diagram form first. Okay. Right, so let's look at A intersect B. This is the set of all elements which are in A and also in B. So in the contained case, A and B would be the region which has both elements from both sets. In the disjoint case, A and B would be completely empty. There'd be nothing. There's no element that's in both of these. In the case with some common elements, the common elements would be in A and B. The next case is union, so A or B. Okay, so in the contained case, A or B, or I think of it as A with B, is a set of all points which are in one set or the other, or both. So in this case, it's unaffected. In the disjoint case, it would be the sets in A, the points in A, the points in B, those together. It doesn't matter that they're not connected. That is the result of the union. In the third case, it would be both of these together. So A or B, including the common point. Okay, now A minus B, A without B, is all the points which are in A and not in B. So here would be everything excluding the B points. Here there would be no result because everything in A is in B. So when we remove B, we also remove everything from A. Here it would just be A because there's nothing from B. And here it would just be the points in A, or the elements in A, which are not in B. Okay, so having done these examples, let's describe the set operations in set builder notation. So if I look at A and B, I'll define that to be the set of points satisfying the condition that the point is in A and the point is in B. Okay, with OR union, A union B will be the set of points satisfying the condition X is in A or X is in B. And this isn't an exclusive OR. It could be in both. That's perfectly fine. And then finally, we'll say A minus B will be the set of points where the point is in A, and the point is not in B. Okay, cool. As well as this, we have De Morgan's laws. Let's have a look at those. So De Morgan's laws are as follows. If I take the union and complement it, so I find the opposite of that, that is the union, the complement of A and the complement of B. So let's think about it. If we are not in the set of either A or B, then we have to not be in A and we have to not be in B. And similarly, the complement of the intersection is the complement of A union complement of B. So if we are not in both A and B, then either we're not in A or we're not in B. Okay, let's prove this a little more rigorously. Let's prove the second one of these. So the way I'll prove this is I'll start off, I'll say let X be in this left-hand side. Now this is equivalent to saying, okay, X is not in A and B. We can say, therefore, well, if it's not in A and B, this does seem like a little bit of a circular argument, but we're going to appeal to it. If X is not in A and B, then X would not be in A, or X would not be in B, and therefore X is in A complement, or X is in B complement. And this tells us we have X in here implies X in here, so then this tells us that A and B is a subset of this. Okay, so that's one side. Then we'll go the other way. We'll say now let X be in this one, the right-hand side. This means that X is in A complement, or X is in B complement, and then equivalently, that means X is not in A, or X is not in B, and therefore X is in the complement of A and B. This tells us that A complement union B complement is a subset of that. So because the subset works both ways, we have therefore the two sets are equal to each other. This may seem a little contrived, but I think it's important to go through an example of showing equality of sets by getting the two subsets. So that's sort of it for the main concepts. We can leave it here, but I am going to go through a few exercises just to hustle, just to work on it and really drive it home. So again, these are from the course material, the textbook that I'm working through. Let's say that we have some A and B, and both of these are subsets of sort of a universal set, like omega, if you've done probability theory. It's common to use omega. Let's go with this. So we'll say, first of all, we'll prove A is a subset of B if and only if the union reduces to B. Okay, so with an if and only if, we have to prove both ways. So we'll go, it doesn't matter which way we go. We'll go the right way first. So we'll say, let A be a subset of B, i.e. any element being in A implies that element is in B. Okay. We say then A union B is the set of points which is in either. But note, we have X being in A implies X is in B. So this condition here sort of reduces to X in B or X in B. And then if we have the set of points which are all in B, well, that's B. Okay. Then we'll go back and we'll prove it the other way. So I'll say, okay, let's go the other way. Okay, so we'll let A union B be B. All right. Okay, so we'll say now let X be something in A, because what we want to show is we want to show A as a subset of B. So we want to start off with X is in A, and then as a consequence, X must be in B. So if X is in A, then X will be in A union B, because this is all the points in A, all the points in, or all the points in B, and A union B is equal to B. So therefore, we started with X in A, and we showed that therefore X must be in B, and then we get A is a subset of B. So that's it. We've proved it both ways. We've proved that left-hand side implies right-hand side, and then we started with the right-hand side and showed that that implied left-hand side. That's the if and only if. Okay, another exercise. Let's say I want to show that the complement of A is a subset of B if and only if A union B is our universal set S. Okay. So let's go this way first. So we'll say let A complement be a subset of B. In other words, if something's in A complement, then that something is in B. And then we'll say for all elements of S, either that element is in A or it's not in A. Fair enough. Now, if that element is not in A, then because A complement is a subset of B, that element must be in B. Okay, well, then for every element in S, either it's in A or it's in B. So in other words, the union of these two will construct S. So we say, therefore, A union B holds all the points of S. Okay, now let's go the other way. So we'll say A union B is S, and it's going to be pretty much similar because we're just reversing the steps. So we'll say, okay, well, similarly, we'll say if some X point, which is in S, is not in A, then that point must be in B, because it's still a point in S, so it needs to be covered by one of these sets. Well, if it's not here, it has to be here. But wait a second, this is the statement of a subset. We have X in A complement, whoops, implies X in B, and that's the subsets. We have A complement is a subset of B. And there we are, we're done. Okay, another one. Let's say, can we prove that A being a subset of B implies that B complement is a subset of A complement? Well, yes, we absolutely can. Have a look at this. We have X in A implies X in B. Well, contrapositive. The contrapositive goes P implies Q is the same as not Q implies not P. Okay, so let me give an example here. Simple example. If it's raining, there are clouds. This is equivalent to if there's no clouds, it's not raining. Okay, that's what we're doing here. So the contrapositive, not this bit, so X not an element of B implies X not an element of A. In other words, it should be both ways, shouldn't it? It wouldn't matter. It would work the other way. But yeah, it goes both ways. Now, because of the contrapositive, this is an equivalence statement. And so that actually directly gives us our result. Okay, last example for this video. I know it's getting a bit long, but here we have it. Consider three sets, X, Y, and Z. Let's let X be a subset of Y, and let Y be a subset of Z. Now let's prove that Z without Y without X is equal to X with Z without Y. That's a bit of a mouthful. Now, on the left and right hand side, these are both sets. So we might be tempted to do like a subset argument. Say this is a subset of this, and then say this is a subset of this. Reverse it. We actually don't need to do that. Let's just go with straight equivalence statements. So I'll start on the left hand side. I'll say Z minus Y minus X is equal to Z and not this stuff. So this is another way to do set subtraction. Z and not this stuff. Okay. And we'll apply that definition again. So we'll have Y and not X. And then we'll apply De Morgan's law on this bracket here. So we have not Y or not X, which just goes out to X. Okay. And then we will apply distributive law. So we'll have Z and not Y, or Z and X. So this is set subtraction. And then here it looks a little different, but remember that X is a subset of Z. So if we have Z, X is somewhere inside it, and so the intersection of them is just X. And there we have our result. Anyway, hopefully that was interesting. Kind of see how we're bringing together what we've done so far, as well as, yeah, the previous video. And yeah, that'll be it. Have a good one. See ya.